Hi, in this video, I'm going to discuss about the solutions for the questions asked in the cycle test for the section H. Similar solving procedure can be employed for other sections problem also. So we had two sets, one is set A and set B. So I'm going to discuss the questions on set A first. This is the question for the set A. So there's a sealed tank at 300 Kelvin. It contains gas mixtures, hydrogen, methane, and then carbon dioxide. And the respective molecular weight is given in the bracket. The partial pressure of the gas is given in the question. So we are asked to find the mole fraction, average molecular weight, and density of the mixture. And also they are given us the R value, the gas constant. The problem involving conversion of mass fraction to mole fraction or vice versa can be solved by this tabular format, which helps in minimizing the mistakes we make during the problem solving. So we form a table, we list out all the given data and fill the table first. So first column is for listing all the components in the particular system. In this case, it is hydrogen, methane, and carbon dioxide. The data is given in terms of pressure. Whenever we are asked to convert mass fraction to mole fraction or mole fraction to mass fraction, we need to have in terms of mass or moles. When we solve problems with respect to gas mixture, the data can be given in terms of volume and pressure as well. In this problem, we are given with partial pressure data in atmosphere unit. So the hydrogen is 2 atmospheric pressure and methane is 3 and the carbon dioxide is 1. For solving this problem, we can assume the system obeys ideal gas law. In the ideal gas mixture, the mole percentage will be equal to pressure percentage as well as volume percentage. In this data, we are given with pressure data. So we have to find the pressure percentage and that is equal to mole percentage. Once we got into mole percentage, we can convert to mass fraction easily. So now we are given with pressure data. So now we can convert that to pressure percentage first. So summing up all will give me the total system pressure, which is 6 atmosphere. Now to find the partial pressure percentage of each component, we have to find the ratio of individual pressure by the total pressure multiplied by 100. So in this case of hydrogen, it is 2 by 6 into 100, which gives me 33.33. Similarly, I calculate for methane and carbon dioxide. So 3 by 6 and 1 by 6, which gives me this percentage. So now as per the assumption, mole percentage will be equal to pressure percentage. Since we already calculated the pressure percentage, we can equate that to mole percentage. On assuming the basis as 100 moles, that is 100 moles are in the system, 33.33% will be of hydrogen. So since we have 100 moles, so we can directly say that 33.33 moles are hydrogen, 50 moles of methane, and 16.67 moles of carbon dioxide is present in the system. Now we got the data in terms of moles. Now it's easy for us to convert to mass with the help of molecular weight. So the molecular weight of hydrogen is 2. Methane and the carbon dioxide is filled here. The data is given in the question paper itself. The relation of molecular weight, mass and number of moles can be rearranged to find the mass of the substance. So mass is equal to molecular weight multiplied with number of moles. For hydrogen, the number of moles is 33.33. So we are multiplying with 2, which is a molecular weight, we'll get 66.66. Similarly, I can calculate mass for each component here and I have to sum all the components. You can refer to the videos why we are summing up all these values in the previous video. Now I found the total mass. The total mass is 1600.31. Now to find the mass fraction, so I have to find the ratio of mass of each component with the total mass of the system. For hydrogen, it is 66.66 and the total mass is 1600.31. So the ratio will be 0.04. Similarly, I calculate for other two components. For methane, the ratio of 800 and 1600.31 is 0.5. Similarly, 0.46 for carbon dioxide. Now we have found the mass fraction, number of moles, total mass and total number of moles also. The next step is to find the ratio of total mass by total number of moles, which gives us the average molecular weight. In this case, 1600.31 divided by 100 will give me the average molecular weight because it's a mixture of different gases. So we have to find only the average molecular weight. So in this case, the average molecular weight of this gas mixture is 16 gram per gram mole. The last step is to find the density of the mixture. So the formula is pressure of the system into molecular weight divided by the product of R into T. In the question paper itself, they given what R to be used. As we already discussed in the previous video, the R value should be chosen based on the units of the given data. So now the pressure is 6 atmosphere into molecular weight, that is average molecular weight. We just calculated the average molecular weight, 16 gram per gram mole. The R value is given in the question itself, 0.08206 liter atmosphere per mole Kelvin. The temperature should be substituted in Kelvin and it is directly given in the Kelvin itself in the question. So we are just directly substituting 300 Kelvin in terms of temperature. So on solving, we'll get 3.9 gram per liter, which is the answer for this problem. Moving forward, we'll solve the problem on set B question paper. So a 20-liter gas mixture at 1 atmosphere and 298 Kelvin contains the following gases. So it's a gas mixture problem. So 6 liter of nitrogen, 9 liter of oxygen, and 5 liter of argon in the mixture. So now I want you to note down that the data is given in terms of volume here, and it is a gas mixture. We are asked to calculate the mole fraction of each gas, average molecular weight of the mixture, and computing the density. The R value is given in the question paper itself. As I already told you, solving the problems on mole fraction to mass fraction or vice versa can be solved easily without any mistakes in this table manner. To solve the problem, let's make a table. In the first column, let's fill with all the given data. In this case, the first will be components of the system. So we have oxygen, nitrogen, and argon. So the volume is the given data here. So I'm filling the volume data. So for oxygen, it is 9, nitrogen, it is 6, and argon, it is 5. The data is in terms of volume. That is, so I'm first summing up and finding the total volume. So in this case, we can assume it's an ideal gas mixture. For ideal gas mixture, the mole percentage is equal to pressure percentage and volume percentage. Since the data here is given in terms of volume, if we find the volume percentage, we can equate that volume percentage to mole percentage. Once we find the mole percentage, we can directly calculate the mass fraction. So from the given data of volume, let's find the volume percentage. To find the volume percentage, the volume of the component divided by the total volume into 100. In case of oxygen, 9 by 20 into 100, which gives me 45, which is the volume percentage of oxygen. Similarly, I can calculate for nitrogen and argon, which comes to be 30 and 25 respectively. So now, as we already discussed, volume percentage can be equated to mole percentage. So I have copied here. On assuming basis is 100 moles, that is, assuming there are 100 moles are present in the system, 45% mole percentage of oxygen. So 45 moles of oxygen is there, 30 moles of nitrogen is there, and 25 moles of argon is there. So total is summed here. It comes to be 100, obviously. Now, to convert this number of moles into mass or mass to mole, we use molecular weight. So in this case, oxygen molecular weight, nitrogen and argon is given in the question itself. I have filled the molecular weight data in the table now. So the formula is the mass of the substance is equal to molecular weight multiplied with number of moles. The number of moles is 45 for oxygen and the molecular weight is 32. So I will be getting 1440 as the mass of oxygen in the system. Similarly, I calculate for nitrogen and argon, which comes to be 840, 998.75 grams. So the sum comes to be 3278.75. Now we found the mass. To find the mass fraction, we find the ratio of mass of oxygen and total mass of the system. In this case, 1440 divided by 3278.75, which is total mass, which gives me 0.44. Similarly, I calculate for nitrogen and argon, which comes to be 0.26 and 0.30. So we solve the first objective of the question. Second objective of the question is finding average molecular weight. The average molecular weight can be calculated by finding the ratio of the total mass of the system and the total number of moles in the system. So in this case, the total mass is 3278.75 and total number of moles is assumed to be 100, which is equal to 32.79, which is the average molecular weight of this gas mixture. Now to find the density of the mixture, we have to use this formula. Pressure is 1 atmosphere of the system, which is given in the question. And the average molecular weight we just calculated, which is 32.79 gram per gram mole. And the R value, which is given in the question, of course. Then the temperature, which is 298 Kelvin, which is 25 degrees Celsius. So I am substituting in 298 Kelvin itself. On solving, I'll get the value of density is 1.34 gram per liter. Thank you.